Lab 3, and the aim of this lab was to determine the mass of the black hole by using observations of the orbital motion of a visible star. I applied the momentum principle to position data of the star to find the net force on the system, and then I applied Newton's universal law of gravitation to work out the mass of the black hole. I made the assumption that the net force on the star was due to only a single force from the surroundings, the gravitational pull of the black hole. I found the mass of the black hole to be approximately 2.38 times 10 to the 31 kilograms. In the Python code, I entered the system properties which have been provided, so the mass of the star, the position of the black hole, and the time interval between data points. Here, we instruct Python to import the position data for the star from the CSV file provided. In this while loop, we use the position data to calculate the velocity of the star as it travels along its trajectory orbiting the black hole. In this while loop, we find the initial and final velocities, then use these to find the initial and final momenta. This allows us to calculate the change in velocity and the change in momentum. We define dp dt as delta p over delta t, and we use the momentum principle to relate dp dt to Fnet. This is the momentum principle, and from it we see that Fnet is equal to dp dt. We know that Fnet can be broken down into two components, the parallel component, Fnet parallel, and Fnet perpendicular. Similarly, dp dt can also be broken down into its parallel and perpendicular components. This is the parallel component of dp dt, since here we are taking the change of the magnitude of the momentum rather than the direction, which informs us if the object is slowing down or speeding up. This is the perpendicular component, since we are taking the direction of the momentum, so we can see if the object's trajectory is curving. In the code, we can find the direction vector p hat by dividing the initial momentum vector by its magnitude. We can find the magnitude of dp dt parallel by taking the change in the magnitude of momentum over time. Then we multiply these two together to find the parallel component of dp dt. We can use the momentum principle to find the total force in that direction. So, Fnet parallel is equal to dp dt parallel. Since the vector dp dt is equal to the sum of the parallel and perpendicular components, we can just use vector subtraction to find dp dt perpendicular. Then we can use the momentum principle to connect dp dt perpendicular to Fnet perpendicular. To find the mass of the black hole, we need to use Newton's universal law of gravitation, which states that there is an attraction between all masses in the universe. We can rearrange the gravitational law to find the unknown mass of the black hole. This here given is the actual Python code used. The first line calculates r, the distance between the star and the black hole. The second line is the rearranged formula in Python code, and it finds the mass of the black hole. Now we just need to run the program. Notice that the arrows are largest when the star is closest to the black hole. This is because we assume that the only force acting on the system is the gravitational force, which is inversely proportional to the distance it acts on. The black sphere represents the black hole, and the green line shows the trajectory of the star. The black arrow represents the parallel force. The blue arrow, representing the perpendicular force, shows the direction in which the trajectory curves. At every instant in time, this blue arrow points towards the center of the kissing circle. The yellow arrow represents the net force on the star, so the gravitational force, and it always points towards the black hole. The mass of the black hole is calculated to be approximately 2.38 times 10 to the 31 kilograms. What does it mean? We can derive from the momentum principle that Fnet and dp dt are equal to each other, and so are their parallel and perpendicular components. dp dt tells you how the star moves. It does not affect the star's motion. It can be calculated from position data gathered from observations, You can find dp dt by using the changes in velocity and the formula given. Fnet does affect the star's motion. It cannot be measured directly, but it can be calculated by simply adding up all the forces acting on the system. In this case, it can be calculated using Newton's universal law of gravitation. What if? What if you replace the black hole with a different black hole in the same location? The motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. In this case, you would not be able to tell the difference. It is not possible to find a value for the mass of the new black hole that is different from the mass you found for the original one. This is because the original position data for the star is the same, therefore you would get the same velocities and momenta and the same net force acting on the star due to the gravitational force. The mass of this new black hole would have to be the same as the mass of the original. Thank you for watching.